Okay. So, today we discuss something which is a very important concept in the domain of probability theory. It is called a rigorous mathematical treatment to these is actually beyond the scope of this course. Okay, so, we will not follow this, but we will take we will first state the fact, then explain it maybe through examples, and then try to construct a kind of just not a proof, but some kind of logical basis for the central limit theorem. I repeat, proper mathematically rigorous proof or treatment is beyond the scope of this course. Now, this says that suppose we have got some random variables x 1, it has got some probability density and distribution function. It could be Bernoulli, it could be binomial, it could be Poisson, it could be Gaussian. It has got a mean mu 1, variance sigma 1 square. Similarly, suppose we have got another x 2, mean mu 2, variance is sigma 2 square, dot 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 dot, we have up to x n, and I tell you x they may not be same type of random variable, that is the probability density of x 1 could be different in nature from the probability density of x 2. For instance, x 1 could be a normal variable, x 2 could be uniformly distributed variable, x n could be say Poisson distributed variable, likewise. So, their density and distribution functions can be widely different. Okay, we are taking n such random variables, and this has got mean mu n and variance equal to sigma n square. What is given is that this x 1, x 2 up to x n, they are statistically independent. Okay, x 1, x 2, x n, they are statistically independent. Each random variable, say x I, has a mean mu I, variance sigma I square. Then, if we form a sum like this, okay, we know that probability density of x is actually speaking, it is the convolution, the probability density function of x is the convolution, maybe I call it P 1, P 1 stands for the probability density of the random variable x 1. So, P 1 x 1 convolved with P 2 x 2, P 2 x 2 is the probability density function of the random variable x 2. So, P 1 x 1 convolved with star stands for convolution, convolved with P 2 x 2 star dot 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 star P n x n. This we know from the theory of characteristic functions, or in terms of characteristic function phi omega, okay, is nothing but product phi 1, phi omega is the characteristic function of P x. I do not know whether I wrote phi j omega or phi omega, maybe phi j omega, I am not sure. In any case, it is a function of omega only, it is not a function of j. We just write j omega because j and omega come together. Okay. This is a product of phi 1 j omega dot 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 phi n j omega. This is always true, but what central limit theorem says is really very interesting, and is several steps ahead of this. It says that suppose we take many such random variables, that is n, that is the total number of random variables is quite large, theoretically n approaching infinity, practically n is say very large. In that case, the summation x will become closer, will tend to be very close to a Gaussian distribution. The probability density of x will tend to be very close to a Gaussian density function. Of course, the mean of that will be the mean of the summation, and variance will be the summation. If x has mean mu and variance sigma square, then it will be the probability density of x will be a close approximation of Gaussian density function of mean mu and variance sigma square, irrespective of whether x 1 is Gaussian or uniform, x 2 is or Poisson or something else. Okay. Similarly, x 2 could be I mean, it does not matter whether x2 is Gaussian or of some other, it has some other probability density function, so on and so forth. If we add up many such random variables, then the resulting probability density function tends to be a close approximation of a Gaussian function, Gaussian distribution. Of course, there is a condition, I am coming to that, but before that let me just state this mathematically. That is, firstly, mu, that is mean of x, obviously is equal to mean of x 1 plus mean of x 2 and then dot 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 and then mean of x n. So, this is nothing but mu 1 plus mu 2 plus dot 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 mu n. So, if we know the mu, the mean of each of the random variable, we know what is the mean of x. That is again irrespective of the individual density and distribution functions. Okay. Mu is always the sum of the individual mu's. Similarly, we have seen earlier that since x 1, x 2 up to x n they are statistically independent, the variance sigma square, that is variance of x is nothing but sigma 1 square plus sigma 2 square plus dot dot plus sigma n square, just the summation of the variances. So, we formed a random variable x by summing n number of such random variables and we take n to be very large, theoretically tending to infinity, practically very large. Okay. In any case, the mean of the resulting sum is always sum of the individual means and variance of the resulting sum, that is x, is nothing but sum of the individual variances, that is always true. So, mu and sigma square give you the mean and variance respectively of x, that we know. Then the central limit theorem states, as we already discussed, I am just putting it mathematically, it states that p of x, if n tends to infinity, that is n is very large, p x will tend to a Gaussian curve, a Gaussian density. Okay. Of mean mu, variance sigma square. Of course, this is true if the probability density of each random variable is insignificant. I mean, everybody has a significant presence. That is, it's not that, I mean, if you take n to be very large, it's not that just a finite subset of those random variables x 1 to x n, maybe m of them only dominate in terms of the density, and the other n minus m, their probability density are, their functions are very narrow, okay, very narrow and very localized. So, they hardly dominate. In that case, it will not be. What I mean is that suppose you take, as I said, we have got x equal to x 1 plus x 2 plus dot 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 plus x n. Okay. It means that what I am trying to say is this: the probability density of each x I should be significant. By this is a just pure English statement. By this, actually what I try to mean is that the probability distribution should be a well spread out function. It will not be a very narrow and localized function and all that. That is, over the axis, if you take the x axis, it's not that over the major part of the axis it has no presence and is therefore dominated by other density functions. Okay. If that be the case, then only p x will tend to this. What I mean by this is, suppose, as I said, x equal to x 1 plus x 2 plus dot 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 x n, okay, which means p x, as we know, p x 1 convolved with p x 2 convolved with dot 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 convolved with p x n. Now, if it so happens that out of this n random variables, many of them, maybe odd number of them are not significant, in the sense that they are localized, they are like impulses, like maybe p x I is an impulse. There is, if you integrate it, you get 1, but it is localized here. such functions I will call to be insignificant, because over the entire x axis they are hardly present anywhere. They are dominated by other probability density functions which are not of this type. This is only present at a particular point, okay, at a particular point, maybe a, b, whatever. So, this kind of functions should not be present. I mean, we should not have random variables which have such very localized and narrow, probability density functions, which we also can view as ones which are weak, in the sense that over the entire axis, x axis, in most of the places they are dominated by other functions. This is not allowed. What happens if I have got an impulse? Obviously, if you have in the convolution, if you just have an impulse, I mean, you get back the, I mean, it makes no difference. Any function convolved with an impulse gives you back the same function. So, that impulse does not make any difference in the output. Okay. Any function convolved with by an impulse function, okay, does not produce any change, it gives you back the same original function. That means, if out of this n probability density functions, suppose r of them are impulsive, that means I can just take them out, because they do not make any difference. Okay. I just can take them out, they do not make any difference, which means only n minus r number of probability density functions are significant, but n minus r may not be very high. In that case, I mean, my statement that I take a very large number of such random variables, okay, it is defeated, because even if I take n to be very large, some of them which have impulsive probability density functions, they have to be taken out. Okay. When you find out the resulting probability density functions, those impulsive probability densities do not make any difference. Okay. So, it is as if only n minus r random variables are present, okay, and n minus r may not be high. So, in that case the central limit theorem may not work, because for this the total number of such random variables which have significant probability density functions, okay, that should be very high, theoretically tending to infinity. So, that means I repeat, central limit theorem will work if total number of random variables n tends to infinity, or in practice is very large. Further, each of them has got a significant probability density, that is over the entire x axis they are present in a major portion, okay, they are not dominated by other probability density functions in most of the part of the x axis. If that be the case, then this central limit theorem exists. Now, this is a qualitative description. Actually, there is a rigorous mathematical theory for it, okay, that we will skip. But here at least through this convolution expressions we made our point clear, that if some of the random variables has just impulsive probability density functions, then they do not make any contribution to p of x. Whether you have the random variable or not, okay, the probability density of x does not change, because it is given by the convolution of the rest of the functions. So, such insignificant probability densities do not create any difference. So, I should not have such random variables which have such impulsive or very narrow or localized kind of probability density functions, okay, which we can say equivalently that probability density functions which are dominated in this x axis in most of the part. Such random variables are not to be included here. Okay. In that case, if n is large, then probability density of x, p of x approaches a Gaussian function. Okay. Now, this is a very useful theorem. This is used, I mean, this is used in many contexts. In fact, often it helps us in making assumption, like this, that given a random variable which may be coming, as a superposition of various random observations, we can treat that random variable to be Gaussian without much problem, by virtue of this central limit theorem. And once more, and of course, x 1, x 2, x n, they have to be statistically independent. This whole convolution relationship is based on that. Okay. Let us take an example. Suppose we have got the random variables x 1, x 2, dot 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 x n. Each of them, actually they are IID. We say IID. It means independent. So, they are mutually independent, statistically independent, and identically distributed. So, they have the same density function, same probability distribution function, they are called IID. Suppose in this example x1 up to xn, they are IID random variables and their density is uniform. That is, given that say pi xi is something like this. This is t, this is 1 by t. So, area is 1. Okay. So, first, what is the mean? What is mu I? Of course, mu I will not depend on I, because this is true for each I, all these IID. So, each xi has the same distribution, identical distribution. Anyway, still I write mu I. So, what is mu I? Mu I is of course, as you know, x into px, that is xi pi xi dxi, okay, and xi should be from minus infinity to infinity, and this is very simple. We should integrate only from 0 to t, okay, and probability density here is 1 by t. 1 by t can go out. And xi dxi. So, xi square by 2, d square by 2, then t. So, basically t by 2. Obviously, from just from this figure itself we can see that since the density is constant from 0 to t, average will be t by 2. So, you get t by 2. What is sigma square? Sigma square is nothing but xi minus mu I whole square pxi dxi from minus infinity to infinity, and integral will be from 0 to t xi minus mu I is t by 2. Then you can say xi minus t by 2, you can call it xi prime. That is this simple exercise, but I can leave it to you, leave it for you to work out, but nevertheless we do it first here. Xi minus t by 2 into 1 by t by 2 whole square into 1 by t whole square into 1 by t dxi. You call xi minus t by 2 as xi prime, it is just a shift of origin. So, this integral, this 1 by t comes out, integral is from minus t by 2 to t by 2, and sorry, you call it xi prime, and easily dxi and dxi prime are same. So, I again call it back as xi, so xi square, or you can keep it, you can call it xi prime also, but no, you can as well again write the same symbol xi, though it is a different xi now, dxi. So, if you integrate xi cube by 3, okay, so t cube by 8, so what happens? Xi cube by 3 so 1 by t so xi cube means if you put the limit t cube by 8 and 3 24. So, twice that t cube by 24 into 2. So, essentially t square by 12. So, sigma square is t square by 12. Okay, I go to the another page. Now, suppose I form first x is equal to just x1 plus x2. Obviously, sigma x square is nothing but sigma x1 square plus sigma x2 square, but each of them has got how much? T square by 12. So, sigma x square is t square by 6, and mu x is nothing but mu x1 mu x2, earlier I call it mu y. So, maybe I stick to the same notation. And t by 2 there is t. Okay. So, x 1 x 2 each of them is uniformly distributed, and if they are added they are statistically independent IID, and x therefore has variance t square by 6 and mean t. What is the density of x? It is not uniform of course. So, what is probability density of x? That will be nothing but, that is p x is nothing but p 1 x 1 convolved with p 2 x 2. It so happens that since these are IID, p 1 and p 2 they are the same function, that is the uniform density function. So, I can as well say p x 1 convolved with p x 2. How does the convolution look like? I know p x is such that the mean that we will get out of it is t, and the variance that we will get out of it is t square by 6. But what is the density function? Okay, you have to convolve. So, how do we convolve? One function is like this, 0 to t and then 1 by t, and other function, if we just reverse, you have to reverse it. So, it is like this. First you reverse it like this, 0 to minus t. So, now there is no overlap. If you now shift it to the left, shift this to the left like this, the overlap between this and this is 0, and therefore, area of the overlapping region is 0. Okay. So, you will get 0 output. That means, to the left of this you will have 0, and now if I shift it to the right, that is, suppose this is now shifted to the right, like this. So, then this is the overlapping area. Okay. And if you actually convolution of two rectangle is triangle, we all know. So, what is the area of this? Area is, if you had advanced by say x, okay, if you have advanced is by this much x, then how much is the area? X into 1 by t. So, x into 1 by t, and this as x increases and goes up to this capital T, this point, area increases. So, it is a linear function with slope 1 by t. So, till x takes the value t, this goes up like this with a slope 1 by t, slope 1 by t, because area is x into 1 by t. Then suppose I am here, x has come up to this place. This is x. So, now as it goes further and further to the right, the overlapping area, that is this much, this decreases. So, and finally, a time will come when this rectangle will come out, that is when x is to the right of twice t, this rectangle will be going out, it is so far going out to the right. So, that there is no overlap between the two rectangles, and area is again 0. Okay, so that happens at x equal to 2 t, and obviously, you can see that is at 2 t, from 2 t onwards output will be 0, because when x is at 2 t, this rectangle is just somewhere here, and the overlap is 0, and as it moves further to the right, that is as x increases further and further, overlap still continues to remain 0. So, to the right of x equal to 2 t, I always have the value 0, and to the left of 2 t, between t to 2 t, I see that the area, like here, this area actually, this part, this area will be decreasing as x becomes higher and higher, because rectangle will be sliding further to the right. So, overlapping area will be less, okay. And obviously, you can see that area This will be a linear function actually, like this. It is a linear function, that is not very difficult to see. If this is x and total length is t, okay, you know how much this side is, you know this is 1 by t. Okay. This is x, total length is t, and this point is t. So, this is you know this is x minus t. So, how much is this? Two t minus x. Okay, this length is twice t minus x, and therefore, it will fall down. You can easily see. So, it is a triangle. It is a triangle function. Okay. Okay. How do you know it is 2 t minus x? It is very simple. Suppose I had repeated this, suppose hypothetically I get up to 2 t and this is x. So, this gap is 2 t minus x, right, and just from symmetry you see is a repetition, this portion and this portion they are same. Okay, it is a periodic repetition. So, 2 t minus x. So, 2 t minus x times 1 by t, 1 by t is the height. So, there is a negative slope of minus 1 by t. So, it falls down. Okay. Now, so this is the actual probability density, but if I plot now a Gaussian probability density with mean t and variance t squared by sigma, how does it look like? If I plot a Gaussian distribution with mean t, then it will be like this. Something like this, mean is t, okay, and it will touch the top because Gaussian at mean is okay. I mean it will be somewhere here. Okay. So, you see it is following the Gaussian curve is now following somewhat this triangle. Now, if I instead of having just two random variables x1 and x2, suppose I have got another x1, x2 and x3, and we again do the same exercise and find out what is the resulting probability density, we will find, we will be doing it now, we will find that the resulting density is a further closer approximation, or it becomes closer further to a Gaussian curve, so on and so forth. Okay. How do we do that? We have seen already that if you now call it x prime as x1 plus x2 and x equal to x prime plus x3, which is nothing but x1 plus x2 plus x3. Now, we have already seen p x prime, if you say it is a triangle function, mean is t, center is t and goes up to 2 t. We also know what is the mean of x prime, that is mu 1 plus u 2, what is the variance of x prime, sigma 1 square plus sigma 2 square, this we know. Now, x, so obviously mu x will be mu 1, that is mu 1 plus mu 2 from here from x prime, and mu 3, and sigma x square will be from x prime it is sigma 1 square plus sigma 2 squared, and then from x 3 sigma 3 square, they are all statistically independent IID. Okay. So, just a summation of means and summation of the random variances. Okay. What is the actual density? Actual density will be a convolution between p x prime, maybe I can call it p prime now, because it is no longer uniform in appearance. So, it is a defined function altogether. So, what is P x? P x is nothing but P prime x prime, I put it P x x, okay, P prime x prime, where P prime is of this form, convolve with P x 3, where P x 3 is just uniform derivative which we have seen earlier. How does it look like? So, you have to convolve here. P x 3 is uniform. So, to convolve we have to first reverse it as before. At this moment there is no overlap, and as so this is the, this point is the x, as x becomes, x goes to the left of origin, this entire rectangle moves to the further to the left and there is no overlap between the two figures. So, you continue to get 0 value. So, as before to the left you get 0. Actually, as we know in signal processing that convolution of any two causal functions gives you a causal function. The same thing is happening here. The probability density functions, whether uniform or triangular or whatever, they are all causal here, causal functions. So, naturally convolution also will give rise to causal function. So, to the left is 0. Now, to the right what is happening, this bit interesting, that suppose it is somewhere here now. So, this part is the overlap. Okay. I have to find out the area of this, multiply by 1 by t, I get some value, but that area, if this is x, height will be 1 by t times x, 1 by t is the slope. So, x into 1 by t x, that will be a quadratic function, x square by t. So, you will get a function like this, okay, something like this. Then as this rectangle goes further and further into it, the area increases. Finally, when it is exactly here, that is x is t, then I have got the maximum overlap. Okay. I have got t into 1 by t, that is 1, it goes up to 1. After this, what is happening? If this goes further to the right, suppose I am somewhere here, what is happening from this side, I am cut off here only, okay, but here I am having something like this. So, from this side a smaller triangle is going away, but from the right hand side a bigger trapezium is coming in. So, area still increases. So, it will still increase. When will it stop? When will it reach maximum? It will reach maximum somewhere here, when I guess x has gone somewhere here. I mean, let me draw. When that rectangle has come here and that this point t is in the middle, at this point it reaches maximum, and this rectangle tries to move further to the right, then what happens? You get a trapezium from right hand side of smaller area and a bigger triangle goes out. Okay. So, the area starts falling, that is, if I now goes further like this, then from this triangle a bigger chunk will go away, okay. And earlier you had this much, now a smaller portion will come in. So, naturally area will fall down, and this will continue at then what happens when x is here? Then there is some overlap, same thing, you get value 1, and now as x this starts going out to the right, area will fall down, because you will only be losing, no new area will be added, but area will be, some portion of the triangle will always go out. Okay. So, it will start falling, and finally, when x has gone to thrice t, there is a 3t, it will appear 0, because that time there will be just no overlap between the triangle and this thing. So, this is like this. So, t 2t, okay. Now, here mu 1 plus mu 2 plus mu 3, how much is that? Each of them has been t by 2. So, this is 3t by 2, and 3t by 2 is somewhere here, this is 3t by 2, right. This is the mean. And what is the variance? Variance is t square by 12, t square by 12, t square by 12. So, how much is that? T square by 4. So, this is equal to t square by 4, this is equal to 3t by 2. So, t square by 4. So, if I now plot a Gaussian density function e to the power minus x minus 3t by 2 whole square divided by twice sigma square, and sigma square is t square by 4. So, twice into t square by 4, that makes it t square by 2. Okay, t square by 2, and 1 by root 2 pi sigma, and sigma is nothing but t by 2. How will it look like? That will be even closer. That Gaussian density will be even closer to this, it will be almost on this. So, you see, as we added one extra variable x 3, okay, we get even a better, even a further closer approximation to a Gaussian curve. So, this is the meaning of the central limit theorem, that if x 1, x 2, x 3, they have densities which are not dominating, one is not dominating the other. Okay. In that case, if you sum them and if you sum many of them, and if they are statistically independent, then the sum tends to become a Gaussian random variable. Okay. One result follows from this. That is, suppose we have got this Bernoulli trials, that is, we are just tossing a coin n times, x I is related with the x I is a random variable, it is related to the ith toss. If x I is, if the ith toss gives rise to head, x I takes 1, if ith toss results in head, equal to 0 if ith toss results in tail. This has probability p, this has probability q, and p plus q equal to 1. Okay. And these tosses, they are mutually statistically independent, as you can see, and you just form a random variable by summing them and summing many of them. Okay. Now, what is mu I here? What is mu I? Mu I means x I can take value 1 with probability p. So, 1 into p and value 0 with probability q. So, 1 into p plus 0 into q, which is nothing but p. And what is sigma I square? Sigma I square, when it takes the value 1, so its deviation from mean is 1 minus p. So, square of that times the probability of 1, that is p, and when it takes the value 0, then deviation from mean is 0 minus p square into probability q, and 1 minus p is nothing but q. So, this is q square p plus p square q. You take p q common, p plus q, and p plus q is 1, which is nothing but p q. Okay. So, that means mu x is nothing but n times p and sigma x square is nothing but n times p q. We have already seen what is the exact probability density for x, that is, say, what are the values x can take. X can take either 0 when each of x 1, x 2 up to x n takes 0, that is always tail occurs. Then a head occurs only once and tail occurs on rest of the occasions. In that case, x takes the value 1. Then 2 means head occurs twice and rest of the occasions you get tail, and likewise. So, it can take, x can take, as I said earlier, values either 0 or 1 or 2 up to n. Okay. So, p of x equal to k, we have seen earlier, is nothing but is that binomial distribution n c k p to the power k q to the power n minus k, that is the actual definition. But going by central limit theorem, if n is large, that is this, there should be approximately equal to 1 by root 2 pi square root, sigma square is p q. So, sigma x square is n p q. So, square root n p q e to the power minus x minus n p whole square by twice n p q. This result has a name. This is called Laplace de Moivre theorem. Okay. Now, an outline of the proof, I mean, I do not have that much time to carry out the proof, but let me get into it. So, instead of calling it a proof, I will rather call it justification, because it is not really a proof in the strict mathematical sense. Okay, it is just logical way of justifying the central limit theorem. Okay, it is just a logical approach. That is, I will call it now. Before that, I just modify the things a bit. Instead of taking the variable x I, let me take it as x I minus, first x I minus mu I. So, then it will have this variable will have mean 0, and then if I divide it by sigma I and I call it x I prime, then x I prime is a random variable with mean 0 and variance 1. Okay. Such x I primes are suppose added. So, suppose x is nothing but x 1 prime plus x 2 prime, sorry, then central limit theorem wants us to prove that P of x for large n, P of x will tend to, what is the mean of x then? Mean of x is obviously, what is the mean of x? Okay. I am just, I will change it a little bit, I will not, maybe it will be better if I do not divide by sigma I, but rather I divide it by sigma. I will tell you what sigma is. Sigma square is nothing but sigma 1 square plus sigma 2 square plus dot 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 plus sigma n square. Okay. So, if you add up all the individual variances, you get the variance sigma square, and suppose x I define to be x I minus mu I by sigma. So, obviously, x I prime, no, x I prime I mean defined to be like this. So, obviously, x I prime has 0 mean, at least that much is sure. So, x also has 0 mean, and what is the variance of x? Because x, these are statistically independent. Okay. X, I mean x 1 prime will have a variance is equal to sigma 1 square by sigma square, x 2 prime will have a variance sigma 2 square by sigma square, dot 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 sigma n square by sigma square, and if you add all of them, then you get 1. So, x will be a random variable with 0 mean and variance 1. Okay. Now, in that context, central limit theorem would say that for large n, probability density of such x should approximate this function x square by 2, sigma is 1 and mean is 0, should approximate this. This is what we have to prove. Okay. So, remember I am talking of our x, which consists of several random variables which are statistically independent having 0 mean, variance of this form. Okay. So, that the total summation is again a random variable with 0 mean and unit variance. Okay. This is what we have to prove. First, we consider, we will be doing it in the this domain, I mean using characteristic functions, and since time is short today, I will be able to just go into it halfway. I will continue from here in the next class. What is happening? We have to just recall certain things from characteristic function theory, that is, what is phi omega? It is nothing but p x e to the power minus e to the plus d omega x dx minus infinity to infinity. Okay, and then we defined the second characteristic functions phi or maybe no, we defined second characteristic function psi omega as nothing but ln phi omega. Similarly, we had phi is a more general function e to the power s x dx and psi s was ln phi s, right. Okay, this we have seen, this is just repetition. Then phi s can be expanded in Maclaurin series. What is psi 0? That is ln phi 0. What is phi 0? Just integral p x dx, which is 1. So, phi 0 is 1, that means psi 0, which is ln of log of 1, that is 0. So, psi 0 is 1. So, this Maclaurin series will be nothing but psi 0 first, which is okay. Sorry, this is 0, log of 1 is 0, phi 0 is 1, integral p x dx, that is 1. So, log of that is 0, that is psi of 0 is 0. So, Maclaurin series of this will be what? Psi 0 first, which is 0. So, forget it. Then one term, maybe we can call it lambda 1 s, then another term maybe lambda 2 square by 2 s square plus further term. What is lambda 1? Lambda 1 was psi prime, this typical Maclaurin series, psi prime is at psi equal to 0. What is lambda 2? Psi double prime is at s equal to 0, this is Maclaurin series. Okay. What is psi prime s? We have to see. We have done this earlier, but still it is worth we do it again. What is psi prime s? We know that phi s, I mean psi s is ln phi s, or phi s is e to the power psi s. That means phi prime s is nothing but psi prime s times e to the power psi s. So, psi prime 0, and we know e to the power psi 0 is 0, e to the power 0 is 1. So, this is nothing but psi prime 0, and what is psi prime 0 is phi prime 0. What is phi prime 0? First, what is phi prime s? If you differentiate this integral with respect to s, what do you get? X times p x e to the power s x dx. If you differentiate this with respect to s, x comes out. So, x p x e to the power s x dx, and then put s equal to 0 means e to the power 0, that is 1. So, x into p x dx integral, which is nothing but mean of x. So, phi prime 0 is nothing but mean of x, that is the mu. Okay. But in our example, we are considering a random variable x, which has 0 mean, because all the constituents x 1 prime up to x n prime, they are having 0 mean. So, in our case it is 0. So, that means lambda 1, which is nothing but psi prime s with s equal to 0. So, that is 0. So, this goes, this is 0. We consider this term. What is lambda 2? Lambda 2 is this. I do not think I will be able to complete it today, but I will just quote a few, just do a little bit and then call off. I will start from here next class. Just bear with me for this. Okay. What is lambda 2? We have seen already earlier. What is lambda 2? That is, we know that phi prime s we have seen is nothing but psi prime s e to the power psi s. If you differentiate again, phi double prime s is nothing but psi double prime s e to the power psi s, take that outside, and psi prime s whole square e to the power psi s. Put s equal to 0. If you put s equal to 0, e to the power psi s, that is e to the power psi 0, that is equal to 1, because psi 0 is 0. So, 1 psi prime 0 we have already seen is 0. So, forget that, because our mean is 0. So, only psi double prime s, that is psi double prime 0, that is nothing but phi double prime 0, that is phi double prime 0 is nothing but psi double prime 0. And what is phi double prime 0? Okay. What is phi double prime s? You differentiate it once, x into p x e to the power s x. Differentiate again, another x comes. So, x square p x e to the power s x. Now, put s equal to 0. So, just x square p x dx integral, which is nothing but variance of x, because x has 0 mean. So, that is variance of x. So, this is nothing but sigma square. Okay. So, lambda 2 square gives us the sigma square of the random variable. Okay. So, this is for psi s. So, how is psi j omega? You just replace s by j omega. So, you get minus sigma square. So, what is psi j omega? This is nothing but minus sigma square by 2, sigma square omega square by 2. Okay, minus sigma square omega square by 2, plus other terms, of course, higher order terms, but you know we am now considering omega very close to the origin. So, then higher order terms which have higher powers of omega, so omega to the power 3, omega to the power 4, suppose we ignore them. So, then it can be approximated to be like this. Okay, it can be approximated to be like this. So, I will stop here today. I will continue from here in the next class. Just remember this, that around origin, for a 0 mean random variable around origin, the psi j omega can be approximated as minus sigma square omega square by 2. I again repeat, for any random variable which has 0 mean and variance sigma square, the corresponding second characteristic function psi j omega can be approximated around origin by a function like minus sigma square omega square by 2. This is irrespective of whatever be the probability density of the random variable x. So, I stop here today. From here, Okay. So, we will start. Okay. So, today we begin a new topic altogether. So far we have been discussing random variables. Say one random variable, then two random variables, then multiple random variables and all that. Okay. And of course, there are probability density functions, probability distribution functions and various relations and properties associated with them. Now, we use those concepts to now explain or to interpret various natural phenomena, and that takes us to the study of random process, or also called, which is also called stochastic process. What is a stochastic process? Essentially, you remember how we define random variables. I mean, there was some experiment, it is not that it could be a really experiment, but it is just a kind of, it is just a axiom that, okay, I mean, there is an experiment and there are various outcomes that are coming out depending on the trial, and with each outcome you assign a value to a variable. So, that variable is then called a random variable. Similarly, suppose we have got some experiment that is going on, and every trial there is some outcome, okay, and with each outcome is, there is first experiment, then maybe say theta is a set of all outcomes S. S is a typical outcome. So, whenever a particular outcome, an experimental outcome, I mean, when a particular trial takes place, you get some outcome S, and depending on what you get, you assign a value to the variable x, and that variable is called then a random variable, right, random variable x. But instead of assigning a value to the random variable, suppose depending on the outcome S, we generate a function x of t, okay, a particular function. That is, we assign, instead of assigning a value to this outcome S,